Welcome back, focused learners. I am absolutely thrilled to have you here today for this explainer. We're about to embark on a pretty grand journey to demystify what is, quite literally, the operating system of our entire universe. Yep, we're talking about physics. Let's just jump right into it.
So here's our game plan for today. First, we'll answer what is physics, then we'll break down the branches of physics, explore beyond the boundaries, unpack the scientific method, and finally, we'll look at physics in the real world. All right, Section 1. What is physics? The fundamental science of the universe.
Now, what's really fascinating to me here is the sheer scale of this definition. A lot of times people think physics is just a bunch of dry equations on a chalkboard, right? But it's not. It's literally the fundamental framework of, well, everything. It strives to explain how the entire universe works. We're talking everything from the absolute smallest subatomic particles just dancing around in the quantum realm, all the way up to the most massive galaxies spinning out there in the cosmos. It's the framework that defines where things are, when they happen, and how they interact with each other. It's honestly the ultimate pursuit of how and why. And honestly, this quote brilliantly illustrates just how mind-bending these relationships can be. Back in the 20th century, Albert Einstein completely altered our view of the universe with one single realization. You probably know it as the famous equation E=mc². He basically declared that mass and energy aren't just somehow related, they are literally forms of each other. Think about that for a second. An object's mass is essentially just supercondensed energy. It's concepts exactly like this that show us physics is really about tearing down our everyday assumptions to discover the hidden truths of reality.
Moving on to Section 2, the branches of physics, from classical mechanics to the quantum realm.
So, because the universe is so incredibly complex, we kind of have to divide our study of it into distinct branches just to make sense of it all. First up, we have what's generally considered classical physics. And hey, try not to think of these as some boring laundry list you have to memorize. Instead, think of them as different lenses through which we can view the world. For example, mechanics is our lens for motion. Heat and thermodynamics? Those let us understand energy transfer. Acoustics is the physical study of sound. Optics looks at the behavior of visible light, and electromagnetism explores this intimate, invisible dance between electric currents and magnetic fields.
The really crucial point here is how these branches map directly to our tangible, everyday world. Like mechanics is based on things like Newton's laws of motion. It dictates the gears in any mechanical system, determining exactly how physical effects influence motion. Meanwhile, heat and thermodynamics are the literal rules governing the engine of your car. They deal with the thermal energy that materials possess and how that energy is powerfully utilized when it flows from one body to another. But, as our scientific tools improved in the 20th century, our view of the universe expanded right along with them. Enter modern physics. This is where we tackle the incredibly fast, the incredibly small, and the overwhelmingly massive. We've got branches like quantum mechanics and particle physics dealing with the atomic and subatomic levels. Then you have astronomy and cosmology exploring the distribution of celestial bodies and the evolution of the universe itself. And let me tell you, these modern branches, they will often completely defy your common intuition. Actually, let's take a look at this incredible concept and see how it builds on Einstein's earlier breakthrough. Relativistic mechanics completely shatters our traditional understanding of space and time. It explains that space and time aren't absolute quantities at all. They are entirely relative to the observer. So gravity isn't just some mysterious, invisible pull, it's the actual curvature of space-time caused by massive objects, like stars and planets. Basically, gravity and speed literally warp reality as we know it. Crazy, right? Okay, Section 3, Beyond the Boundaries, the interdisciplinary nature of physics. Now, physics doesn't just exist in a vacuum. Because it is the fundamental science, it actively bleeds into other fields, and that fosters some incredible out-of-the-box innovation. Take biophysics, for example. Here, we apply principles of physics to understand biological structures, like the actual mechanics of your DNA. But if you flip that scale all the way around, we have astrophysics, which applies those exact same physical principles to understand celestial bodies and energy in deep space. Think about how wild that is. The exact same fundamental laws govern both the microscopic cells in your body and the giant distant stars in the sky. And this brilliant interdisciplinary approach, it literally saves lives. Medical physics applies physical principles directly to health diagnosis and treatment. The MRI scanner is the perfect example of this. By utilizing the principles of electromagnetism and quantum physics, doctors can look right inside the human body without making a single incision. It's just a profound reminder that understanding the fundamental laws of nature leads directly to life-changing technologies. Section 4, the scientific method, the engine of discovery. So we've talked a lot about what physics is, but how is it actually done? Like, how do we arrive at these mind-bending truths? Well, the answer is the scientific method. It's essentially a rigorous, step-by-step detective story. We always start by identifying an issue and making an observation. Then we propose an educated guess, which we call a hypothesis. Next, we perform an organized experiment to test that guess. If the data repeatedly backs it up, we formulate a theory. And if that theory withstands wide-ranging, intense tests over a long period of time, that's when it becomes a recognized scientific law. Let's look at a really concrete example to make this stick. How do we know for a fact that light travels in a straight line? Well, we start with a simple observation. Opaque objects cast shadows. Our hypothesis based on that, light travels straight. So to test this, we can literally just line up 4 pieces of cardboard, each with a little hole punched in the middle. When they're perfectly aligned, we can see a torchlight shining through all of them. But if we displace even one of those cards, the light is immediately blocked. This organized, repeatable process gives us undeniable proof, elevating a simple guess into a verified physical property. Which brings us to a really crucial question, and I want you to genuinely think about this for a second. What exactly distinguishes a true, rigorous scientific theory from just a simple, pretended belief? How do we actually separate the real science from the pseudoscience? The answer lies in a concept introduced to scientific philosophy called falsifiability. For any theory to be considered truly scientific, it has to stick its neck out. It must make specific predictions that can actually be experimentally tested and, crucially, this is the most important part, potentially proven false. Vague, non-specific, or completely untestable claims, they have absolutely no place in physics. Science isn't about blindly trying to prove that you are right. It's about rigorously trying to prove yourself wrong and seeing what actually survives the test. All right, let's bring it home with Section 5, Physics in the Real World, Thermal Expansion All Around Us. Let's bring all these high-level concepts back down to earth by looking at a highly tangible, everyday application, thermal physics. You see, when a substance is heated, the particles inside it gain kinetic energy. That means they start moving faster, they collide way more forcefully, and they spread out. This action physically forces the entire material to expand in length, area, or volume. We call this phenomenon thermal expansion, and as we're about to see, ignoring it is a total recipe for disaster. This right here is exactly where physics meets engineering to save lives. Think about steel railway tracks. They get incredibly hot baking in the summer sun. Because of thermal expansion, that solid steel is actually going to grow. If engineers didn't understand physics and they failed to leave these small, crucial expansion gaps between the rails, the tracks would literally bend and twist under the immense pressure. It's a terrifying phenomenon called sun kinks, and it would easily derail trains. Actually, the exact same principle applies to those jagged expansion joints you drive over on highway bridges. And hey, thermal expansion applies to gases too. Just consider a hot air balloon. By firing a burner and heating the air inside the balloon, the gas molecules speed up and expand. Because the overall volume increases, but the actual mass stays exactly the same, the hot air becomes less dense than the cooler air outside. This simple, fundamental physical effect creates lift, allowing us to literally float up and conquer the skies. So, as we wrap up our journey today, I really want to leave you with this final, provocative thought. If mastering the basic rules of physics allows us to explain the invisible bending of light, engineer bridges that can survive the intense summer heat, and build machines that literally peer inside the human body, what unseen mysteries of the universe will the scientific method unravel next? The universe is just this massive, grand puzzle, and physics gives us the toolkit we need to solve it. Keep asking questions, keep testing your reality, and thank you so much for joining me on this explainer.